All right, if I will have you follow along here really quickly, one of the things that I see a lot of people still have not managed to do is get VirtualBox installed and running. We are going to use that multiple times throughout this rest of the semester. So whether you're behind, ahead, whatever, you have to have this installed. We're going to actually install, hopefully partly today, another version of an operating system in there. So if you're in the lab here today, please go to ubuntu.com, and we're going to actually download the server version here in the lab really quickly so we can go through some of the steps on how this is going to work. So, because it will take a little bit of time, I'd like you guys to start downloading it now once we have this many people. So notice there are lots of different types. There's server, there's a desktop. So if you will click on downloads, and we don't want the desktop, we've already downloaded that, hopefully. We want the server. And the server, the one we're going to look at, is the 16.04.3. That matches closer all of our descriptions and what we're going to work with. The latest version, if you're living in the server world, you rarely want cutting edge. So we're going to click download. And if you notice, the desktop version wanted you to grab all kinds of extra things, pay a PayPal donation. The server version doesn't ask you to do that. It just simply says, yep, we're going to download. So if you'll notice down here, I've got about 10 minutes left. So as more and more of you grab it, you'll also notice it's very small compared to Windows that you've downloaded, which was almost 4 to 5 gig. And if you downloaded the Ubuntu, the desktop version, it's also very large. The server version's pretty small. It's under a gig. And the reality is, part of that is because it's what we call headless. It doesn't have a GUI, or a graphic user interface. And this is what most of the world lives on. When you go out to a website and it's all pretty and fancy, on the back end, about 80 to 90% of the websites are actually handled with some version of Linux, and they're based on servers that are sitting there, and they don't have a fancy web interface. They're all based on the command line. So we're going to introduce you to that command line this week. And so notice already by the time more and more of you start grabbing that, my download time goes up because, again, we're on a shared bandwidth, a shared pipe in here in the laboratory. So this week is actually, once again, 2 weeks put together. And part of that is, I know that we had Labor Day this week, and we've got some content I want to spend some time on in terms of now we've kind of had some overview, some basics. Now we're going to get into some details about some of these things. So last year's videos are on here. There is also a routing video that is good to watch. It's about 16 minutes long. You are certainly welcome to watch that. There is actually a newer version of that video. This one covers the basics pretty well, and I actually like it's one of the better ones I've found out there that's explains some of the routing concepts that we're going to go over. So we start looking at, in this case, we're going to look at one chapter. We're going to cover it in about 3 class sessions or about a week and a half of time. There are some assignments we're going to do. And to start out with, we need to kind of set a preface. So while I really hate lecturing completely over PowerPoints, I want to start on this idea and get some of these pieces set up so we have them in place. So by now, everybody should have gotten their book. If anybody still doesn't have a book, you're getting further and further behind. Make sure you get it. The ebook is only $26 if you get the ebook. You also need Lab Connections. Lab Connections goes along with this. I do not check them every week, but you probably got either an email saying, hey, congratulations, thanks for buying it, or you got the, hey, you need to go buy this and get out there and find it. Now, the good or the bad thing is I don't pull grades out of Lab Connections until the end of the semester. So, depending on how you want to look at it, that's either good or bad. If you're somebody who needs that constant prodding, I'll kick you in the butt every week, but there's not going to be a grade moved over. There's no connection between Blackboard and Lab Connections where it moves your grades over automatically. The other side about Lab Connections is you can do them unlimited times. We have it in practice mode where you can do them over and over again. The first couple of chapters really are nothing more than an extra quiz. And in fact, you'll probably find some very similar questions to the quiz if you went through Lab Connections as to what was on the actual quiz. It's just trying to get you to read the textbook. Now we're getting a little further on. You're going to start seeing there's more simulations and things that we can't necessarily do in class, or we don't have the tools to do, and especially when we have students scattered around the globe. Cancel. I don't care that you're not really authenticated. All right. So we've talked about this IPv4 and IPv6, and we talked about TCP, Transport Control Protocol / Internet Protocol. And we said these are languages. And so now we're going to start digging into that idea of what is this language, how does it really work, what kind of things are in there. And so we're going to look at some tools we can use. We're going to look at how this actually functions and what that data actually looks like. So the reality is it's a whole group of different languages or protocols that are all bundled into these items. So we're going to look at things like ARP, Address Resolution Protocol, UDP, IP, TCP. And so one of the greatest benefits to all of this is this stuff is open source. In other words, the language behind it and how the formatting is done is all open source. Nobody controls it other than a group that says you can use it. There are other networking protocols that have failed now, and we've went past them, but they were controlled by a vendor. And if a vendor said, hey, you have to do this, you would have to do it. In addition to that, it cost a lot of money. This is essentially freeware in terms of these applications. So whether I own a Mac, whether I own a PC, whether I come up with my own new computer company, I can use these tools and I can use the methodology, how they're written, how they're done, no matter what we're doing. So it has a couple of things. When it says routable, what I mean when I say routable, so internally we looked at those ports, and those ports I could communicate with another computer in this lab, but it wasn't routable. In other words, it has to change from one type of LAN, so our continuous LAN here, and it goes to another LAN somewhere else. And so it can be routed or moved around the internet. And so that ability to get all over the world is that idea of routable. And here's where we look back. We have that OSI reference model. So the way I always remember it, programmers do not throw sausage pizza away from top to bottom. So the top is that thing that you actually interact with. So the application layer you may interact with fairly directly. So you may open up ipconfig or another tool. It acts at that application layer. And at that application layer, it's got a payload. And we have, all right, here's some data, but it doesn't do us any good. We can't do anything with it. This is how we transport it to another machine. And so if I come down here to the transport layer, and I look over here at this encapsulation model, we start getting what we call a segment, and it gets a header in front of it. So we add some metadata, data about your information. So you may have the world's greatest CD of music, and so you have a song. And so think about that song. That title of that is that metadata, that, in this case, that header. We then move down to the next layer. So here we go from transport to network, and as it moves down, this had data and then a header. That all becomes the payload or the packet for the next segment down. And then we add another header. So this is the header for all of this data, and then finally we call it a frame. And a frame really means it wraps around it. So a window frame wraps around that glass. That's what we're really doing. We put a header and we put a trailer on it. So there's now metadata encapsulating or enclosing all of our payload. So now if it's our music or it's our song or whatever we want to think about it, now it's got a header and it's got an ending piece. And we can send it out over whatever physical medium we use. So if it's in here, it goes out over a wire. Maybe it comes off your laptop and goes into a wireless. Maybe you're connected directly into a fiber optic backbone. However it happens, it hits that physical layer and it gets sent to its destination. At its destination, it does the reverse of that. So it starts stripping off those headers and the trailer and finally comes back up and says, here's my payload. So here's that song that you wanted to listen to, and we stripped it back off. And the reason we have to do that, what are we actually sending? Are we sending different numbers, or are we sending just ones and zeros? Can we do anything other than ones and zeros in our computer? No. So everything we send is ones and zeros. And there's a whole chunk of them. And so we have to figure out how we send it. How do I know how many ones and zeros are in that audio file? I don't have any idea. So now we have to come up and figure out how do we send that data. So this is just a little more detailed explanation. So they call them layers 7, 6, and 5. Remember, we have names for them. And I think it's easier to remember the names. But what we're really doing is layer 4, we're adding a port number. And a port number is not routable. So at number 4, we could send data around our network here in our lab by that port number. Now remember, we had 65,536 of those. Well, we could send data around with that port number, and to the receiving app, they would know, but we don't have any way to identify that computer yet. And so we need to figure out where that host or that computer is coming from. So finally we get down to level 2, and we're adding that entire encapsulation. And then layer 1 is that area where that physical layer where we take that packet, that frame that we've created, and we convert it into some kind of a physical medium, whether it's wireless, wired. So this is kind of an idea about what we're going to see. And you'll see some of these terms, and you're thinking, I'm never going to do this crap in my life, and yet you're going to see some of these terms over and over again. So where some of these things live depends on the device. And so when we go look at a switch here in our lab, and what runs this lab, we have a switch in there. What layer does a switch live on? What layer does that switch live on? So, layer 2, most switches are what we consider layer 2 switches. A router then is that next layer up. It's a layer 3. And so it operates at that layer. And then a firewall, which you guys have all heard the term firewall, what does it actually do? And we'll talk about that in here, is that firewall lives at layer 4. But these are generic. And so we'll talk about some of these pieces, but generically a generic switch. So if you crawl under your desk, and some of these have a very small little 5-port hub or switch in there, that is just a layer 2 switch. But I can have a switch that we call a layer 3 switch that incorporates some of those routing pieces. I'm like, oh man, why do we need to do that? Well, there's some reasons that make life really, really handy. And in fact, we can have a layer 4, layer 5, and in fact, there are some software layer 6 and 7 switches. But generically, we think of switching as a layer 2, routers as a layer 3, and something like a firewall or a managed device then as layer 4. The most common thing we're going to send. When you guys experimented with Wireshark last week, trying to get some hands-on in that, you probably said, wow, we get different kinds of packets. And one of them I get is something called a TCP packet. So Transmission Control Protocol. So when you hear the words TCP, that stands for Transport Control Protocol. And there is something really weird about this one. It's called a connection-oriented protocol. So this means everything we send in here, we get an acknowledgement back. So we set up a secure channel to send data, and we create what we call a handshake, and everything you send gets an acknowledgement back. So we all have those friends of ours that when we talk to them, we have to say, all right, did you understand what I said? Repeat back to me what I just said, right? Give me directions to the bar, repeat back. My 6-year-old and 7-year-olds, I have to do this. Did you pay attention? Did you get the message? What was the message? That's kind of the same thing TCP does. It actually, every packet you send gets an acknowledgement that, hey, I got it and it's correct. And then how we check it's correct is we do it using sequencing and checksums. So we use a mathematical operation to make sure that everything we sent is identical to what we received. Well, that's good. If I'm sending something very critical, if you're sending your paycheck information, you want that to be accurate, right? So we create what's called a three-way handshake. And that handshake says we connect. It gives us also the ability to do something called flow control. Because we do have pieces on our network that are faster than others. So here in our network, we know that we can max out how much bandwidth or how much capacity we have when everybody downloads at the same time. When we do that, if we didn't have flow control, that Ubuntu server that's sitting out there sending us that file is far faster than anything we have here on our campus. And so it would just overwhelm us and just send scads of data that are just going to get dumped off. But because we have this flow control in there, it can actually regulate how fast it starts sending data. So to do this, we need to look at what's in what we call a TCP segment. So this is all binary. So remember, these are just zeros or ones. They're bits. And so remember, the TCP doesn't have a trailer. It's only got this piece in front of it. And in front of it, we know exactly how long this piece in the front's going to be. And the easiest way we write it then is each line is 32 bits, or the size of a web address in binary. And so what it really, though, is a continuous string of zeros and ones. So we write it this way, but if you think about like a giant number line with zeros and ones, in this case, we can figure out how long that would be because each one's 32 bits long. So 32, 64, 96, 128, and so on. We know how big this piece is before it gets to the data. So it's got a couple of things in it. It's got a source port, so where it's coming from, and a destination port, where it's going to. And that is in binary. So it's 0 to 16 and 16 to 31. So in other words, it's 16 bits. Huh. Well, hang on. Maybe I'm crazy. But if I whip out my calculator and I take 2 to the 16th power, what do you think I'm going to get? What number do you think I'm going to get? You can open up your calculator and check. What number do I get if I do that? What is 2 to the 16th power? What is the biggest source port I can get and the biggest destination port? I can wait. So our calculator has an exponent value. Oh, holy cow. Is that a number I've used before in here? Remember I said about those ports, they're 65,536. That's what that value is. Now, I didn't multiply that out in my head. It just sticks there. But that's 2 to the 16th power. So that's where that value for that source port is sent to us. But every computer in here has a source port, don't they? So if I just sent out just a TCP segment, every computer in here that responds at that particular port is going to get that message. Is that what we want to do? Probably not. So this, at this point, is not routable yet. A TCP segment is not routable. But there's a couple of other pieces in here. So we have a sequence number and an acknowledgement number. So that sequence number, it generates a random number of 32 bits in length and says, I'm going to send this value out. We get an acknowledgement from the other computer that's sending a message back that takes that sequence number, adds 1 to it, and sends it back as the acknowledgement number to us. So we use those to say, is it in the right sequence? We can put these little chunks back together in the right order. We use that acknowledgement to make sure that it gets there. We use this checksum here. So we do a mathematical operation on this entire segment, and we come up with a value, and it says here. And that mathematical operation we can do again. We use the same math on both sides. If I get the same value, then I'm assuming that that packet, that segment, made it through okay. And then we have that data piece. So the data is on the end. Well, almost everything we do, unfortunately, we have to break down into smaller and smaller segments. We don't send an entire song as one big segment. It goes in multiple small pieces. When you talk on your telephone, your cell phone, your regular phone at this point, you don't talk in one continuous piece. It's broken into tiny little segments. And how many of those and how much data depends on what you're sending and what kind of protocols you're using. So this is kind of the basis for what we're doing. So we also need to figure out what this three-step or three-way handshake means. So we have different types of packets. And so notice there were some flags up there before. So if I look at the flags, there's some that say sync and acknowledgement here in this little area here. Those are just little, they flip from zeros to ones, whether they're a sync packet or whether they're an acknowledgement packet. So it just tells us what kind of packet it is. So that three-way handshake then, we send out our first computer. So our computer in front of us, if we're trying to connect to the server in there and you're getting a file off that shared drive. When you do that, you send a request for a connection or a sync packet. You want to synchronize with them, if you want to think about it that way. So you're sending a sync packet. They send back then an acknowledgement and a sync packet at the same time. So they send one saying, I want to sync with you also, and I'm acknowledging that I got a packet from you to begin with. You get that message and you send back, yep, I got your message. So it takes 3 messages to establish that connection before we can send any data. So before we can do anything else, so that sequence number then, so there's a couple of different ways it can happen, but the most common way is it's increased by the number of bits in each received segment, so it quickly becomes the method. We can see how long that message needs to be. There's nowhere in there that says this message can only be 22 bits, except we say here. So this is kind of that graphic, if you're going to create it. So here we have a segment number, and it says, okay, I don't have an acknowledgement. I'm just sending a flag for sync, and it sends it over to the computer B. So this is our server. And the server says, okay, well, I'm going to send an acknowledgement, and notice that sequence number. So it ends in 558. Now it becomes the acknowledgement 559, sends it back towards computer A, and it has a segment number also that it generated randomly. So it sends back an acknowledgement, yes, I got your message, yes, I want to sync with you also, and then computer A has to send this back saying, I am acknowledging that I got your message. So think about how annoying that would be if every time I walked up to you, we had to do this. This happens very quickly, but it is some overhead on a packet. So we're not sending any data until we've sent 3 bits back and forth. We've established a communication path. So we're dedicated to that communication. This is great if it's data that doesn't or can't be altered in any way, because we're also checking that packet to make sure it is completely accurate. If it's not, so if we send back a message that says, nope, I sent a message, until I send the acknowledgement, so my computer over here, if I don't get an acknowledgement back from that server, I'm going to just keep resending my original message over and over and over again until I get that acknowledgement. So if it's one packet that gets dropped, not a big deal. But imagine if my server doesn't ever respond, I just continually sit there and stream it. That's not necessarily good either, correct? So one of the things that people have done to hack or create denial of service attacks is send false messages back requesting acknowledgments. And so they just get hammered by other things. So they've spoofed a packet to make it look like they're trying to get an acknowledgment. So the other side of that then, so if we don't send a TCP packet and we want to send data, we can actually send what's called a UDP, or datagram. So a datagram we think is more efficient. It doesn't take 3 steps before we can send data. So we don't have as much overhead. It doesn't have as much overhead in the packet itself, because remember how much data we had that sucked up just for that overhead? Well, this is what a datagram. It really just says, here's where I'm coming from, here's where I'm going. It does have a checksum, but we don't really use it for much, other than we can check the data, but we don't have any way to get it resent to us. So we can reject it if we know it's bad. But where this is really useful, we want to send a lot of data very quickly, and if one packet out of 1 million is bad, so if you have one packet on your Netflix stream that's bad, and there's a tiny little dot on your screen that doesn't light up correctly, are you going to notice that? No. If it's a financial spreadsheet, yeah, you might notice that. But really great things for audio, video, because we don't have all that overhead, and we can blast out data over and over again. So that checksum, we can use it to drop packets we know are bad, but it's actually optional. We can actually leave it just blank. IPv6 does require it. So something similar in IPv6, just a little more robust. So TCP is robust. UDP is fast, if you want to think about it that way. So I guarantee that all my message gets there on TCP. I don't know if it gets there. I just blast out information on UDP. So the type of data we're going to use makes a lot of difference. But none of that said I can get outside of my own network. None of it could go anywhere other than just blast out to every computer port that was open on port 443 or port 7019 or whatever port we used. So we needed to add another piece. So IP then operates the next level down. And IP says it's routable now. We can travel more than one network segment, one LAN segment. We can go through different types of networks. We can change from fiber to Wi-Fi or to fiber optic to optical to whatever we need to transfer to. But IP by itself is unreliable. It's connectionless. So it relies on that TCP that it's encapsulating to give you that guaranteed delivery. So IP, we're going to look at, just adds onto the top of this. So we're going to add another piece right over the top. And now we're going to add all of this options up here. So this is my original TCP packet. So it's already got a header, but we're wrapping it up inside, so it becomes the data. So what used to be the header now becomes the data for the next piece. And so this is what an IPv4 packet. So when I say packet inspection, or we look at Wireshark and we look at packets, this is what we're starting to grab, is we're grabbing these packets. And again, there's a lot of overhead in here before we do anything. So 0 to 31, so in other words, that's the length of an IP address. And we've got 1, 2, 3, 4, 5, 6 of that. So we have a lot of data being sucked up just in this overhead to send it. But we need some of it because now this is where we add source IP and destination. In other words, where we're coming from and what we're going to. And we know that that IP address is really that address of where we're going to send data. And so we have some other pieces up there. So notice total length. We can have these can be variable length. So that length field tells us how long this whole string of zeros and ones is. And another piece that's really critical to us that we're going to look at is this time to live. So time to live. So all of you have a time to live, right? But you don't know exactly when you're going to keel over and die, right? When we send out a packet, it has a specific death notice. So we can assign it a value that says you can only live so long. But what we really call it is how many hops. So every time this packet touches a router and gets manipulated, that number goes down 1. So if it started at 32, it hit the first router, it became 31. It would go down pretty rapidly. And when it hits 0, when a router gets a packet that's got a time to live of 0, it says, oh, that packet doesn't need to get forwarded anymore. What it really does is sends back a message back to the source and says, hey, your packet died right here. So we can take advantage of this. We can take advantage of this. Well, we know that what we can do is we could send out a ping. But what we're going to do, so if you'll hit the Windows key, we're going to show you another tool. So if you'll type CMD, and it'll pop up on your screen. You don't need to do the administrative one because we're not going to do anything really that's going to change anything. We're going to show you another one called trace route. Now, trace route, though, is spelled weird. So it's trace, and then they abbreviate route with RT. I wish I could tell you why, but... So, trace route. And I just went to Google just so I could put it up here on the screen. And so, trace route says, I'm going to take advantage of that time to live packet. And what this is really doing, remember those pings we sent out earlier? And that ping said, I'm going to find the DNS server, and I'm going to find that for google.com, and I'm going to send one message out and see if I get a response back. What this is doing something similar. So what it first does is send out a ping with a time to live of 1. So the first router it hits converts it to 0, and that router sends back a message saying, hey, your packet died here. It then sends out a packet with a time to live of 2. So it makes it through the first router, and it dies at the next stop on its journey. And so by doing that, we're mapping out where those pings die and where they go to. So in this case, we can see a couple of interesting pieces along the way. You'll get a little bit of information back. Now, because these are part of the beauty of the internet is it's robust, you may get a different result than I did for the same location. These packets do not have to travel the same route, and we'll talk about why. But most cases they do. In this case, it's still sending out. You can change this. It's by default set to 32 hops, I think, or 30 hops. So, a couple of things that happen. So if I notice, the first packet it dies at is my router here. So 192.180.1. It dies, and it says, hey, I got here. The next router is one here on campus at 10.20.208.254. So it hits a router on our campus, and it dies. Next, it hits another router, 192.132.7, Again, I can tell that that's on our campus for two reasons. One, it's in that 192 range, which 192 is private, right? Private, non-routable. So that number says it can't go outside of our network. The other thing is look at the times. So all of a sudden we go from less than 1 millisecond, to suddenly we jump to 25 milliseconds. So where we have that time jump is generally we can tell that some processing has happened. So when I hit a router, it takes some time to process. It also can be a length of how far that cable is. So if I go from here to the administration building, it's pretty short. And the signal on a cable goes fairly quickly. In theory, what should that signal on a cable go at the speed of? Or on a fiber, what should it go at the speed of? At the speed of light. Now, because of something called propagation delay and such, it doesn't actually do that, but it's very fast. And we can tell how long. So we suddenly jump to taking 25 milliseconds. And notice, in this case, we hit Omaha, and now we're at Denver for a route. Sometimes these routers will reveal where they're going. So if I do something like UNL, so I'm going to do the same thing. And remember that shortcut key of if I arrow up, I get the message I had before. So I'm going to change that, and I'm going to look at UNL. And I'm going to go to unl.edu. And what I expect is, to begin with, it's going to be very similar. So I know it's going to hit my router and die. I know it's going to go to the Omaha router for whatever reason. But that's interesting to me for a couple of reasons. Where do you think we actually get our internet service from? Who do you think provides our internet service? I don't know. Windstreams gives us fiber down here, but we actually get internet service through the University of Nebraska-Lincoln. So it's interesting that our traffic then, for whatever reason today, is routing through Omaha, through Denver, through somewhere at Rackspace on a server. And finally, notice it comes back here, and it actually comes back to UNL. So it's interesting that our traffic has to loop around versus going directly when we're looking at that. And you can look at almost any destination, and you can start to see it. If you really want to try one, we can find one overseas. So if we could find a company in Germany or another country, and you look at their router address, and where it's coming from, when you see these times will jump up, and they'll certainly go significantly higher. So we could do it, open up a browser window. So we could come back here, and we could say, what is a company in Germany? So what kind of companies can we find in Germany? List of companies in Germany, and we can probably find a web address. So let's look at the very first one and look at what we have for a web address. So I'm going to look at a watch company. So if I look for this, I can probably find a website. So I'm going to do a Google search here really quickly. I'm going to say, yep, okay. And see if they have a website. Well, they do. So I'm going to put that into my trace route and see if I can see it go overseas. So what I want to do, though, is notice this EN at the end. I'm going to leave that off and try to force it to go to a router in Germany. And let's see what happens there. So if I put the EN in it, a lot of these companies are very smart. And you'll see if we get to actually to Germany, you'll see why, how it happens here. So in this place, this company actually hosts that site, not in Germany, but in what country do you think they're hosting the site in? From those hops, it's hosted in the United States. Because when we go overseas, you're going to see that that time is significantly longer. So what about a company like BMW? So if I know that I have a lot of customers, so I think it's just BMW.com. Maybe it's BMW Automotive. BMW.com. So we'll try that one. Oh. Trace route. So because of that time gap, as it hits and goes overseas, companies that have a large U.S. presence, even if they're a foreign company, often host some of their websites here. And again, BMW is obviously very smart. So it takes a little bit to do that, to find one that's here. What's interesting, though, is both BMW and our watch company both end up at Akaimi, so one of the large aggregators of websites. And so my guess is you'll find that happen pretty often. But if you can actually get to a website overseas or find one, you'll see that that time jumps up. You found one, didn't you? So wargaming.com, and it jumped from 30 milliseconds to 100 plus when it actually goes overseas, or longer depending on where you're at. If you can find a Chinese company, for example, that may not be a bad one to use. So it's interesting to see how they jump and where they actually go to. So is this the only route that those packets can go? No. This is, as of this second, the best path that has been developed for that particular packet each time. So traceroute is a really great tool, and traceroute uses that time to live to create that setup for us. So now we have a source address and a destination IP, so we know where we're coming and where we're going from. So we're getting a lot more data now about what we're going to do. So these are probably the most common packets we're going to do in IPv4. So some of the different pieces in here. So differentiated services says what kind of priority. So we can assign priority based on the type of traffic. So does voice packets need more priority than somebody's high school graduation pictures they are mailing grandma? We've all had a phone call that sounds like you're talking to Mars with an echo, or it drops out. What happens if we start losing too many packets, or they get out of order, or they take too long, is we start having service issues. So this can actually give us a way to give a service level based on our need. So the internet header length, we actually say how long that header is going to be. We say how long our data is going to be. So our total length, the total length of the IP packet, including the header and data, cannot exceed, do I see a number that we've seen before? 65,535. Or, if you remember that, that's 2 to the 16th minus 1. You guys are all like, oh man. But it's a set size. We can't have an unlimited size of IP packet. We're limited to how many bytes we can have in that packet. And in fact, what you're going to find out as we go through here is sometimes we want very small packets because we can send them out much quicker. If we have the longest packet we can get and it doesn't arrive properly, it takes a long time for that to be regenerated and resent in internet terms of time. So sometimes we want very short, very fast packets that we're going to send those to. So again, remember we talked about that IP address being 32 bits or 4 groups of 8 numbers? Well, here it is again. We're going to see that again. And then the data down here. This is the important part, but remember it's also got that TCP packet wrapped up in there, so it's got some additional piece. If I compare that to IPv6, IPv6 is actually a lot simpler. Look at that. yeah, the source address is 4 times as long and the destination is 4 times as long. But isn't this a lot simpler? We should go to IPv6 just because of this. Life is easy. We don't have all those individual pieces. It doesn't have a time to live. It doesn't have all these pieces. It does have a hop limit, which is similar, but life is actually easier on IPv6 in a lot of ways. And so, if you look at some of them, they're very similar. Version says what kind of IP version. Traffic class, so again, kind of like that diff serve. And here we say, this is how long it is, and this is what's going to come next, and how long it's going to live, and then we have addresses, and that's it. It's actually a lot easier in IPv6. The addresses suck to try to remember, but it actually makes life a little easier. So we have to have some way then to communicate about how we send those packets. So we've got an address now. We haven't yet figured out how that IP address gets assigned to our computer quite yet, but we're going to get there. And we've got an address, we know where we want to go, and now we really need to figure out how do we get there and how do we know if we can get there and how do we start routing that packet. Because as you saw, even to get to UNL, which, we can all drive to UNL, but how does our computer find the address and find those packets? We need some kind of a methodology for that. And so one of the things we use is something called Internet Control Message Protocol. So whoever started some of these networks really had a love for the word protocol. So the protocol for this, protocol for that, it really just means a language. And so ICMP can actually do a lot of things. So it can tell us when networks are congested, when a packet doesn't reach its destination. So in other words, what gets sent back when that ping dies or that each piece of that trace route is an ICMP message and says, hey, you're dead. So one thing it does, so it does send about failures, but notice what it doesn't do. It doesn't fix any of them. So it just kind of like the flag waver. And I've seen a funny commercial for a dentist, actually, that they're coming in and going, well, no, I'm just the dental monitor, and it's for a fraud reporting services, and it's kind of the same idea. This kind of waves and says, hey, there's a problem, but it doesn't fix anything. So same like a dental monitor tells you got a cavity, but doesn't fix the cavity. This is one thing we can do. All right, so by now, let me jump out of here real quick. By now, all of you should have downloaded Ubuntu, the server, right? So I'm going to quickly go through there again. And everybody should have VirtualBox on these machines already in the lab. So we've downloaded it, and we can double check. It should be in our download folder, so I'm going to click. And there's a shortcut key. What's the shortcut key to the folder? If I hold the Windows key down and I hit E, what do? It pops up my File Explorer. So I'm going to come over here, and if I look under Downloads, I notice I've got an Ubuntu version of Server downloaded. So everybody should hopefully have that. That one's pretty small. And notice it even says it's a disk image type. So Windows 10 can actually open this. So I could actually open it up and look at the files inside of there. I don't want to do that. Go backwards one. I want to know where it's at. In this case, it's at this PC and downloads. Got it. So I'm going to get that out of my way. I need to launch VirtualBox. VirtualBox. And it's probably on your screen. If not, you can type VirtualBox. And in the lab, it may say there's a new version. Just go ahead and click, yeah, whatever, and X out of it. It may let you click OK. In this one, I wiped them all off, and I don't have any VirtualBoxes up there right now. So I'm going to have to click New. When I start typing Ubuntu, I'm going to type Ubuntu Server so I know what it is. I'm also going to do something else. I am going to add my username and password that I'm going to use for this system right up front. And the reason I'm going to do this is I want to try to remember it. This isn't exactly a safe process if you would allow multiple people in there, but for this, so we can remember it, there is no way to recover a password in Ubuntu easily. So I'm going to remember this one, and I'm going to put CMIS Lab as the user, and I'm going to create a password, capital PERU2017 exclamation mark in there. So I'm going to use that as my username and password. I put it right in the name. That way I can't forget it as easily, right? And I'm going to click Next. The other thing I need to make sure is that I have 64-bit Ubuntu right here. The server version of Ubuntu is only available on a 64-bit operating system. Most of the time that's setting on a server where it's got, in some cases, hundreds of gigabytes of data available. There is really not much need for it on anything less, so a 64-bit operating system is kind of mandatory. For whatever reason, it wants to default this really small. I'm going to go to about 2 gigs or so. So somewhere staying in the green. Depending on which computer you have in the lab, you have at least 8 gigs available, and some of them have 16. So you can go up to 2 to 4 gigs and not have any difference. We're not going to run a lot of services on here, so it doesn't need a ton of memory. If I were going to run this as an actual server and start hosting websites, I would need certainly a lot more data than that. So the rest of those are all the defaults, so I can click Next or Create for everything. So when I first get here now, I want to point out something, because one of the biggest issues we've had is people aren't pointing this to the correct area. And so notice up here it says controller, and it says optical drive. Almost every operating system wants to install by default off of an optical drive. Well, in most of these cases, your computers don't even have a CD drive anymore, and we're certainly not going to burn a disk so you can install off of it. We're going to install off of here, but we're going to do it off that ISO image. And so if I miss it the first time through, I can actually click right here, and I can actually change where this looks at. But since I haven't screwed up yet, I'm going to click Start. And it's probably going to pop up in the other window for me. Maybe it's not even going to pop up on this one. There it is. It's on the other window. All right, so I can't change this for whatever reason in Windows. It pops up in the other window. Because it's a dialog box, I can't change it over to where I'm actually recording. But it pops up, and you guys have all seen that. It pops up and says, select startup disk. And this is where it seems like half the class goes awry. Where it says select startup disk, it's normally set to what's called host drive D, or that CD-ROM that it creates. There's a folder icon by that, and I'm going to click on that folder icon and navigate to that ISO. But I screwed up, or I forgot to do it. And notice I got the warning, no bootable medium found. That just means that I'm not looking at that ISO file. So if I didn't do it correctly there, I can close this. And I'm just going to close this really quickly. And I'm just going to power it off because I don't really want it to start where it's at. And notice I can click right there on optical drive, and I can say choose image. All right, let me choose image. And I get exactly the same option. I get into the file folder. I can go to downloads. I can select the server. Now what I want to see is it says, here's where I'm storing my information. So it's a .vdi file. Up there it's going to say ubuntu.iso. So it is pointed to the correct location. And now when I start it, so if I restart it again, it'll pop up in the other window, I'm sure. Nope, actually stayed over here. Now I get the beginning of the install for the server. So I'm going to hit the enter key because I'm pretty sure I want English. If you would like another language, you can certainly try it. If you're not fluent in that language, it might make it a little harder to do. My first option, and again, my mouse doesn't really work too well in here because this is based on a command line. So I'm really going to be mostly using the keyboard in Ubuntu Server. So this is a little different. So I clicked enter. And in fact, you can go turn those off up top if you want to, if it bothers you, where it says, yes, I'm capturing the mouse pointer. So I'm going to make those go away temporarily. Click, click. All right, so again, choose the language for the installation progress. Yep, I want English. I'm in the United States. Do I want to detect keyboard? No. So again, I'm going to use primarily the defaults for this as I go through. And so it's trying to detect hardware, but it's not very fancy and not very graphical. Remember, this is used in servers. So depending on which survey you read, about 80% to 90% of the world's web traffic actually is on a server like what you're creating right now. So it'll go through. All right, so this host name is what that network is going to see. So in our case, because we're just creating a virtual system, you could call it anything you wanted to. I'm going to, just to make it easy, I'm going to call it Ubuntu Server. Now, if all of us were really installing a server, so we had a giant server rack, and everybody's installing their own machine, we'd have to come up with a clever naming scheme, because if we all had the same name, that's going to cause an issue. So right now, I'm just going to click Ubuntu Server, and I'm going to click the continue. Invalid host name. All right. I apparently put a space in it, and they didn't like that, so I'm going to go back. Ubuntu Server. Now it'll like it. So remember up there, I created a name. This is where it becomes important. So I'm going to put in my name. So I called this one for the root account or the administration account. I called it CMIS Lab, if I can read my script up there. So CMIS Lab. And this username. All right, so I have to create a password. And just because it'll let me, I'm going to type in my password. And one thing that's weird you'll find when working in this, when I type a Windows password in, it shows me the little asterisk as I type along. In here, depending on where we're typing it in, it may or may not. In this case, it does. When I actually enter the password to log into the system, it's not going to tell me that. So I'm going to click continue. Hopefully I typed what I thought I did. Now I'm going to have a couple of more options. So generally we would encrypt the home, but we're not going to now. So encrypt, we would scramble it so other people could not get it. Your time zone is yes. So again, it's going through and finishing its install. All right. So here, this is a little different. Remember, we're configuring a virtual hard drive on there. We're not doing a physical hard drive. So we have a couple of different options that we can do. Well, I'm going to go ahead, just using the default, and go ahead and click enter. And then I get the option of select a disk to partition. So in this case, it's creating an 8.6 gigabyte drive for me a virtual drive. It's not a physical drive. The other issue I have run into with some students is if you are very, very low on hard drive space, you may need to figure out how to either increase something or do that. So write changes. This one I do have to change because if I don't say yes, it's not going to create that drive for me. Amount of the volume, I'm going to click continue. But to get to the continue, notice I hit the tab key or the arrow key to get to the continue. So we're using the keyboard. Write changes to this, yes. So this one takes a little more install prowess. It's not all just defaults. You have to actually read what's going on and look at what you're doing. You are not wiping out the hard drive on your computer, and you are not installing this locally. You're just doing this inside of that VirtualBox. At some point it'll finish this. Oddly, I have the slowest computer in the entire lab sitting up here. So if you're on one of the new ones, for example, and you're following along, you'd actually have this done at this point. So notice it's actually going out on the web. It's made a network connection. It's actually done some updates as it's going through there if you're following along on the messages. It's pulling some updates and grabbing them. All right, so blank for none. We don't need to add a proxy. So if we were really in a server environment where we had a rack of these, we would probably be using a proxy to get back out. In this case, we don't, so we don't need one. And notice again, it's went out on the internet and grabbed some files. All right. This is kind of an odd choice because in Windows, it says, hey, you need to install all your updates automatically. But on this, the preferred choice is don't do any updates unless you do it manually. Why on a server would I want to do it manually instead of letting Windows do it or Ubuntu? So I'm running a website like Amazon. I've got 1 million customers. Everything's working. I do an update and it breaks. Do I have a job the next day? So before we would do updates, we would actually do that on a sandboxed environment and make sure that it doesn't break any of our other software. So the default on a server tends to be we do all the updates manually. All right. We're going to click continue because we're not going to add any of these right now. Anything out of the ordinary. Go little thing. Those of you that have taken programming or are looking at programming here, one of the things I noticed it just installed is Python by default right in there. Because Python we use as a scripting language to control our servers in a lot of cases. Language is going in. Stuck at 97%. Should be doing a reboot right now. No, still more to install. So the bootloader is what allows it to start. Install the grub loader, yes. Installation complete. Now we're going to reboot it. So behind the scenes now you get to see all the processes as they load. And that's it. That's Windows, that's server right there. You get a command prompt. And that is where we're going to leave today. So you need a login. And so if I have a login, I can now get into that server. So that login I wrote was CMIS Lab, I believe. It's going to ask for a password. And notice it doesn't put little asterisks or stars in. It's kind of weird because it hangs it out there all by itself, so you can't even tell you're typing. We're now logged into this server right now, and you can tell that. So it says CMIS Lab at Ubuntu server, and we can start using some of the commands and start working with a little bit of Linux behind the scenes. This is where the web lives. It doesn't live in some fancy graphic interface. It actually lives right here. And so we're going to figure out how to use some of that. All right, so before you're done in this class, because we're going to use them all, you need to have server up and running. You're going to have Ubuntu, the desktop, running. And we're going to look at the differences. And you need Windows 10 or Windows 8, somewhere in a virtual environment we can use that you won't get corrupted or destroyed. We don't want to do some of these things on your live machine. We want to get it in that virtual sandbox, and we want to experiment with what can happen. So there are some additional steps and some things we're going to look at about commands inside of here. But this is really where, if you got a job at Google and they said you're going to manage servers, this is where you're going to live. And you're going to be looking at that. And even behind the scenes, one of the interesting things, those of you especially that have Macs, you have this available, the same thing right here on your Mac. We have something a little different on a PC, but a Mac is really based on a Linux operating system. Did you guys know that, those of you with Macs? Yeah, it's part of the reason it's far more secure is it's based on this. So at this point, we've got that up and running. Read chapter 3 for the weekend. If you haven't, make sure you've read it. Go through there. Those lab connections should be hopefully helping you understand some of the material. We're now getting into some more details. So we talked about IPv4, IPv6. Now we're going to start looking at what it looks like. If for some reason you haven't got Wireshark installed on the assignment for the last couple of weeks, make sure you get that installed, because now we're going to take a detailed look at it and pull up some packets and actually break them apart. See what traffic on the web actually looks like. You kind of got to play around with it. Was the last assignment. Was try this, try this, try this. And the grade was all based on did you actually just install it, get it up and running and working. So now we're actually going to go in and do some content and look at what it can actually do. So this is the Linux server. You are certainly welcome to install it in the lab, but it would be handy to have it on your own machine. And again, these are the three we're primarily going to install. We're also going to install and look at some other virtual machines you can use, but it's really handy to have these because they're also transportable from one machine to another, and we'll show you what that's about. All right. Probably. Are you getting the no bootable medium found? Correct. Then you are not pointing it towards that image file to where it's going to install from. Just like as if you started your brand new computer and it didn't have a DVD drive in it to install Windows on it, that's the same error you would get if you've got a brand new computer that didn't have an operating system on it. So, all right, let me stop the recording before I do anything else.